Good morning, everyone. I'm sorry I can't be with you this morning. I have an appointment that I can't get out of. I would much rather be in school working with you than taking care of this, but as they say, it is what it is. We're going to get started with the final unit today in Math 30-1, which is called Permutations and Combinations and the Binomial Theorem. Just even looking at the graphic on the title page of this handout, you can tell that this is decidedly different than most of the math we've been doing. Most of the math we've been doing has been focused on functions and equations and trigonometry, and this, at least for the permutations and combinations part of this unit, has very little to do with algebra and nothing to do with trigonometry or functions. To begin with here, we're going to be talking today about something called the fundamental counting principle. What we're doing today is we're learning what the fundamental counting principle is and start to solve problems involving applications of the fundamental counting principle. And the fundamental counting principle forms the backbone for most of what we do in this unit. I'm also just going to briefly introduce you to the concept of what's called factorial notation to make our jobs a little bit easier when we work with the fundamental counting principle. To begin with, and this is a warm-up I've been using for years and years, it's actually an exercise designed for elementary mathematics students to get them to figure out how to combine different things together. So Bobby Bear is planning a vacation. That's Bobby Bear. Bobby packs 3 different pairs of pants. He has a blue pair of pants, a red pair of pants, and an orange pair of pants, and he has 2 shirts, yellow and green. So there are his pants, and here are his shirts. And the question is, how many different outfits does Bobby Bear actually have when he takes those 3 pairs of pants and 2 shirts on vacation? We're asked to list all of the different outfits in terms of an ordered pair using the code pants, comma, shirt. This has nothing to do with XY ordered pairs or graphs. It's just a way to abbreviate our answers. So to begin with here, Bobby Bear gets up on the first day of his vacation, and he can certainly put on his favorite yellow shirt with a red pair of pants. The next day he gets up, he really likes that yellow shirt, and it's still in pretty good condition. And now he can wear the yellow shirt with the blue pair of pants. The next day, gets up again, he's going to wear the yellow shirt for a 3rd day in a row because he can now put an orange pair of pants on over the shirt. And the idea is now Bobby Bear has exhausted all of the outfits that have a yellow shirt. And the reason he's exhausted all of the outfits that have a yellow shirt is because we want to know how many different outfits there are. And if he puts on the yellow shirt on the 4th day, he has to repeat. He has to wear a pair of pants with the yellow shirt that he's already worn with the yellow shirt. So on the 4th day, he can put on the green shirt with the red pants. And I'm perfectly aware that most of you probably know the answer to this question without actually watching me do all of these combinations. And I sincerely hope that you're not trying to draw all of these. On the 5th day, he can wear the green shirt with the blue pants, and then on the 6th day, that's the end of his vacation. He's planned things out perfectly because now he's worn all of his different outfits. So he has yellow with red pants, yellow shirt with blue pants, yellow shirt with orange, and then green with red pants, green with blue pants, green with orange. The answer to the question is there are 6 different outfits that Bobby Bear can wear. We're asked to list them in ordered pairs in terms of pants followed by shirts, so we can put R, Y for the red pants and the yellow shirt, BY for blue and yellow, OY for orange and yellow. Then we can go RG for red and green, BG for blue and green, and OG for orange and green. And I don't know the value of writing all of these in ordered pairs. It's just part of the question. Bottom line is Bobby Bear had to do 2 things. He had to put on a shirt and he had to put on a pair of pants, and there are 6 different ways that that can be done. The second part of the warm-up says that you have an ice cream shop in which there are two different types of cones that you can order. You can order what's called a regular cone or a waffle cone. They only have 3 flavors of ice cream, so it's probably not an ice cream shop, it's just an ice cream cart on a beach maybe in Sylvan Lake. And they have 3 different flavors of ice cream, strawberry, vanilla, and pistachio. And there are 2 types of sprinkles you can put on the ice cream, chocolate and mint. And the next sentence is important. A single ice cream dessert, a single order, consists of a cone, 1 flavor of ice cream, and 1 type of sprinkle. You have to choose 1 type of sprinkle, 1 type of ice cream, and 1 type of cone. Complete the tree diagram below to determine all of the different ice cream combinations there are. So the left-hand tree has R for regular cone, and the right hand has W for waffle. So imagine that people start lining up to this ice cream stand, and you have people that want a regular cone. They have a decision to make. They've chosen that they want the regular cone, but they can also make a decision as to which type of ice cream they want in that cone. They can have a regular cone with strawberry ice cream, a regular cone with vanilla, or a regular cone with pistachio. Now imagine that they choose a regular cone with strawberry ice cream. They're at a crossroads again, or a fork in the road, if you like, is maybe a better analogy, that they now have to decide what type of sprinkle to use. So it branches off one more time. And I want to point out to everybody at this point, before we finish this tree diagram, that this path that I'm highlighting in green is one particular combination for an order. You can order a regular cone with strawberry ice cream with chocolate sprinkles. This branch that I'm highlighting in blue is a different combination. It's a different order. You can choose a regular cone with strawberry ice cream and mint sprinkles. If we continue with this, looking at the middle of this tree on the left, a regular cone with vanilla ice cream, you can go ahead and choose chocolate or mint sprinkles. A regular cone with pistachio, you can choose chocolate or mint. If you have the waffle cone, you can choose any one of those 3 types of ice cream, and each of those types of ice cream has 2 options for the type of sprinkle. So I'm going to give everybody a minute to just complete your tree diagram, and then we'll talk about the answer to the question. The answer to the question is 12. And the reason the answer is 12 is because each of these branches from the top to the bottom represents a combination. That's 1. That's 2. That's 3. That's 4. I mean, I could keep going. That's 5. And this one is 6. And the bottom line is if there are 6 different combinations for your order in the tree on the left, there's going to be 6 on the right. If you count all of the paths, you're going to get 12. So the answer to warm-up number 2 is 12. For goodness sake, we're not going to be solving these problems using this kind of method or the type of method we used for Bobby Bear, which is to draw all of the solutions. What we're going to do is use what's called the fundamental counting principle. All of these problems that we've looked at in the warm-up illustrate to us what's called the fundamental counting principle. And the fundamental counting principle is used whenever you have a task that has pieces to it. For example, Bobby Bear's task was to get up in the morning and get dressed. And he has 2 pieces. He has to put on a shirt and he has to put on a pair of pants. When you go up to that ice cream stand, your task is to get an ice cream treat. But it consists of pieces. You have to choose 3 things. You have 3 decisions to make. 1, what type of cone do you want? 2, what type of ice cream do you want? And 3, what type of sprinkle do you want? And the fundamental counting principle says, if there are a certain number of ways to complete the first piece, and a certain number of ways to complete the second, and a number of ways to complete the third, etc., then the number of ways to complete the entire thing is found by multiplying the number of ways to complete each of the individual pieces. Now we're going to go back to Bobby Bear and back to the ice cream stand in just a second, but a couple more notes about the fundamental counting principle. This is really crucial in this unit, that the word and means multiply. So when you talk about Bobby Bear had to put on a shirt and a pair of pants, and that's why we could use the fundamental counting principle, although you don't maybe know how that's going to work yet. When you order something from the ice cream stand, you choose a cone and you choose an ice cream and you choose a sprinkle. And that use of the word and is the reason why we can use the fundamental counting principle. Just a note that the fundamental counting principle, as I said a little while ago, is taught in the textbook section titled permutations, but we use it to solve permutations and combinations. And I still haven't revealed to you what the difference is between a permutation and a combination. Once again, I might talk about it in this video, or I might wait until the next time we meet. So if we go back to Bobby Bear had to do two things. He had to choose a pair of pants and choose a shirt. And he had 3 pairs of pants to choose from and 2 shirts to choose from. So because he has to do both, because it's pants and shirt, the fundamental counting principle says we just multiply those numbers together and we get the number of different ways that that entire task can be completed. When you take a look at standing in line looking at the menu of the ice cream stand, there are 2 different cones that you can choose from. There are 3 flavors of ice cream and there are 2 types of sprinkles. Because you need a cone and a flavor of ice cream and a flavor of sprinkle, the fundamental counting principle is in play and you multiply the number of options for each of them together, which gives you 12. So that's the fundamental counting principle. And what we're going to do in what I believe is about the next half hour or so is we're going to go through a number of different examples. And there's no way that in this lesson we will look at every possible type of question. They are numerous. So you have to get used to setting up problems in terms of the fundamental counting principle, no matter how familiar or unfamiliar they may be to you. It's all about taking a number of options and multiplying by a number of options. Example 1. How many different ways are there to arrange all of the letters of the word reason? So the word reason has 2, 4, 6 letters in it. And what we're going to do is we're going to draw 6 blanks. And we're going to say to ourselves that unlike Bobby Bear, who had 2 decisions to make, he had to decide on a pair of pants and decide on a shirt. Unlike the person at the ice cream stand who has 3 decisions to make, what type of cone, what type of ice cream, what flavor of sprinkle, we have 6 decisions to make. The first decision is, which letter do we put in the first blank? And then once we put a letter in the first blank, the next decision will be to put a letter in the second blank, all the way down the line until we've completed all 6 of these pieces of the task of arranging all of these letters. Well, how many ways can we decide on putting a letter in the first blank? The answer is 6. I can choose an R or an E or an A or an S or an O or an N. Bobby Bear only had 3 pairs of pants to choose from. We have 6 different letters to choose from. But we have to put a letter in the first blank and, which means times, we have to now put another letter in the second blank. And we're arranging these letters. So if whatever letter I put in the first blank, it doesn't matter. I've used that letter. I do not have it in the pool of letters to choose from anymore. So because we're arranging them, the number that we have left to choose from after choosing the first one is down to 5. And then we will be down to 4, and down to 3, and down to 2, and we don't really have a choice for the last blank, but it will be 1. So there are 6 different options for the first blank, 5 for the second, then 4, then 3, then 2, then 1. And since we have to accomplish all 6 of those, it's and all the way down the line. And you multiply that out, and you get what I want to say is 720. B, how many arrangements of all of the letters of the word reason are there if the arrangement must start with an S? So again, we're going to have 6 decisions to make. We have to decide which letter we put in the first blank, which we put in the second, etc. But this statement here, that the arrangement must start with an S, is called a restriction. And there's a rule when you're dealing with the fundamental counting principle, which is that the restriction needs to be taken care of first. So I prefer to set these up by writing under the first blank, must be an S. And if you want, you could put under the remaining 5 blanks, who cares? It doesn't matter what letters we put anywhere. All that matters is we can't use the same letter more than once. And I guess it also matters that any of those 5 letters after the S can't be an S, because the S has to go first. So we do the restrictions first, and we say, well, how many different options do I have for filling the first blank? And the answer is 1. It has to be an S. And then we can say times, how many options for the second? Well, that's 5, because we have 5 letters left. And then 4, then 3, then 2, then 1. And if you take 5 times 4 times 3 times 2 times 1, you get 120 as the answer. Two, in a classroom there are 25 desks and exactly 25 students. In how many different ways can the students be seated in the desks? So in order to wrap our heads around this, I think it's better if we think of the question this way. If I have 25 students and 25 desks, how many different ways can I make a seating plan? So here are my 25 desks. And essentially, if I want to go about it in an organized way, I can look at this first blank, and I can look at my list of students, and I can decide which student goes there. And the number of different choices I have is 25. Just like when Bobby Bear opens his closet, the number of different choices he has for the pants is 3. Now I go to the next blank. So what I'm going to look at now is this blank. And I look at my list, but now, because I've already chosen one individual to sit in the top left corner of this diagram, I am down to 24. And once again, at the risk of belaboring this, I need to put somebody, one of 25 in the first desk, and one person in the second desk. So because I have to do the first desk and the second, I'm multiplying. Man, I'm not going to write out times 23 times 22, etc., until I get to times 3 times 2 times 1. We know that the answer to this question is going to be the product of 25, 24, 23, 22, all the way down to 1. And I do not want you to write anything else down just yet. I certainly don't want you to write this down, but that's the answer to the question. And if you put that into your calculator will spit out 1.5511210004 times 10 to the 25. And your calculator, of course, I think it only takes 10 decimal places in scientific notation, and then it doesn't show the remaining decimals. I put this into an Excel spreadsheet to see what the number actually is. And I have no idea how to pronounce that. It's 15 something. 15 something, 511 something, on and on and on and on. So in mathematics, when we have big numbers like this, there's a way to abbreviate that. And this 25 times 24, etc., all the way down to 1, is that. And that doesn't mean like 25, like you're surprised or anything. It's pronounced 25 factorial. So 25 with an exclamation point after it means 25 factorial. That's what we call it. That's how we pronounce it. What it actually means is 25 times 24, etc. If I were to go back then and take a look at this example, how many different ways are there to arrange all of the letters of the word reason? The answer to this question is 6 factorial. We don't need to write 720. This 720 and this 6 factorial are exactly the same thing. So on an exam, you might want the answer expressed as 7 factorial, or you might want it expressed as 720. When we take a look at 1b, it turns out that we had 1 times 5 times 4 times 3 times 2 times 1, but this is 5 factorial. So we could have written 5 factorial for this answer instead of 120. Of course, this 1 over here at the beginning of our fundamental counting principle doesn't really change anything. It's 5 factorial. Regardless, the answer to question number 2 is 25 factorial. Let's take a look now at the next example, number 3. A multiple choice exam consists of 25 questions, and they're all A, B, C, D questions. Each question has 4 different choices. How many different sets of answers are there? So what I'm getting at here is I could have an exam with 25 questions in which all of the answers are A. 25 A's would be one of the sets of answers. I could have them all B's. I could have them A, B, C, D, A, B, C, D, A, B, C, D, until I get to the 25th question. So imagine me making an exam, and this is question 1. And this is question 2. This is question 3. And very similar to the previous example with the 25 desks, I'm not going to write all of these out. I'm just going to say dot, 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 and then maybe it's question 24, question 25. So if I make the exam, how many different choices do I have for where to put the answer to question 1? The answer is 4. I can make the answer to question 1 an A or a B or a C or a D. Now, how many different choices do I have for which letter the answer to question 2 is? 4. All of these numbers are going to be 4. And I have to decide on an answer for question 1 and for question 2 and for question 3, etc. So what this is going to be is 4 times itself 25 times, and that means that the answer is 4 raised to the 25. And it doesn't help us to try to put that into a calculator. Even if your calculator can get the value of that, it's probably going to be something so large that makes it unfathomable to us in terms of what it means. It's a huge, huge number. So the answer to number 3 is 4 to the 25. Number 4, a volleyball team is made up of 8 players, and they're going to stand in a line facing the camera for a picture. How many different arrangements are possible? Well, it's 8 factorial. The reason is 1, 2, 3, 4, 5, 6, 7, 8. You have to line up these players, you look across them, and you say, I have 8 different choices for who stands first, 7 for the second, etc. And you know, for goodness sake, at some point we have to abandon this blank thing and say if I have 8 individuals that are going to be lined up in a straight line, there are going to be 8 factorial ways of doing it. So how many ways are there to align, or arrange rather, the 6 letters of the word reason? 6 factorial. If I had 12 books on a shelf, how many ways can they be arranged? 12 factorial. And 8 factorial happens to be equal to 40,320. And now is as good a time as any to show you where you can do that on your calculator. To get 8 factorial on your calculator, you enter 8, and the factorial function is hidden in your math menu. So now you hit math, and it's under the probability submenu, so we can scroll over to the probability menu and find that. I'm just going to wait a minute here to make sure that you're all comfortable with finding that factorial. Once again, you enter the number of the factorial you want, you go to your math menu, scroll over to the probability submenu, and then it's number 4. All right, so that's how many ways to arrange the 8 volleyball players if they stand in a line, and there's no restrictions. The next question is, what if Joan and Emily have to stand together? So Joan and Emily are besties, and they always need to be next to each other. Well, what we need to do is think of the problem in a different way. Here are the 8 volleyball players. We've got Janice, Sophia, Alice, Patty, Becky, Sam, and then there's Emily and Joan. And there are 8 people that need to be arranged in the line for part A of this question. But since Joan and Emily are connected, they have to be next to each other, we have to think of these 8 individuals as 7 things that need to be arranged. Joan and Emily are always being shuffled from position to position, but they are together. So we treat them as one item. We have 1, 2, 3, 4, 5, 6, 7 items to arrange. So, if we take a look at the question, you would normally say to yourself, if you're arranging those 7 items, it would be 7 factorial. That would make sense. How many ways can I arrange these 7 rectangles? Well, 7 times 6 times 5 times 4 times 3 times 2 times 1. However, this arrangement is different than that arrangement. When you look carefully, Emily and Joan in the top arrangement are arranged so that Emily is on your left and Joan is on your right, and in the bottom it's the other way around. So what is it we need to do? In order to answer this question, we have to arrange those 7 items, the 6 volleyball players plus the Joan Emily together, and we need to arrange Joan and Emily. So we have to do 2 things. We have to do them both, so it's and, which means multiply. The number of ways to arrange the 7 items, which are the 6 individual volleyball players, and the pair that's Joan and Emily, is 7 factorial. The number of ways to arrange Joan and Emily is 2 factorial, so we work out what this is. So you go to your calculator, you enter 7 factorial, which I think is 5,040, and I'll double check it. You multiply it by 2 factorial, which is 10,080. We'll just double check here. 7 factorial is 5040 times 2 is this number. So that's the answer to part B. If Joan and Emily must be together, there are 10,080 ways in which that can be accomplished. Now B, I have a feeling this should say C. C says, in how many different ways can we arrange the 8 people if Joan and Emily cannot stand together? So Joan and Emily had a huge fight. Whatever we do when we line them up in the line, Joan and Emily cannot be together. And over the years, I have learned that there's one and only one way to do this problem. What it is to say that Joan and Emily either will be standing next to each other or they won't. Of the, I believe, was 40,320 different arrangements. We'll just go back and look. 40,320 were all of the different arrangements of the 8 players. Of those 40,320, some of them had Joan and Emily standing next to each other, and the rest didn't. If we take the total number of arrangements, this is all arrangements, and we subtract from that the ones where Joan and Emily are joined at the hip, then what we're going to get, and that number was 10,080, what we're going to get is the ones where Joan and Emily are not together. I mean, imagine, this is what I would typically use as an illustration. Imagine there are 40,320 different arrangements, and because you've got no life, you take 40,320 index cards of paper, and on each one you put a particular arrangement. On all of those cards, some of those cards will have Joan and Emily next to each other, and the rest won't. So if you went through that whole stack of cards and you threw into the bin, into the garbage, any of the cards where they were together, you would be left with the number where they are not together. So we need to subtract these two. 40,320 minus the 10,080. That's not right. Minus the 10,080 gives me 30240 as the answer. 30,240. Five boys and 3 girls are arranged in a line. How many unique arrangements are possible if the boys are grouped together? Well, if the boys are grouped together, this is like Joan and Emily, except that there are 5 items that are joined at the hip, figuratively speaking. What we have is boy, 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 boy as one item, and then we have 3 girls. So when you look at this, what we actually have are 1, 2, 3, 4 items to arrange. So we're going to arrange those 4 items, and that number is 4 factorial. That's how many ways to arrange 4 items. Also, though, we need to arrange those 5 boys within their group. We're going to take that group of 5 and put them in different places in the line, but we can also arrange those 5 individual positions in that group, which would be 5 factorial. Working out what that is, I've got a number written down, but I want to double check it. The number I have written down is 2880. 4 factorial, which by the way is 24, times 5 factorial, which by the way is 120. You'll get used to these numbers over time. Gives me 2880. So the answer to number 5 is 2880. Six, consider the letters of the word English. How many more arrangements, 4-letter arrangements, can be formed if you were allowed to repeat the letters compared to if you're not? So if the letters can be repeated, what that means is you can, if you want, you could do that. You have an infinite number of each of those letters. You can repeat them as often as you want. And that means when you talk about the number of options for the first blank, it's 7, because there are 7 letters to choose from. The number for the second is 7, for the third is 7, and for the fourth is 7, because you are allowed to use the same letter more than once. So this works out to 7 raised to the 4. If letters cannot be repeated, then this will be the number of options you have for each choice. You need to choose one of 7 letters for the first blank and one of the remaining 6 for the second, and one of the remaining 5 for the third, and one of the remaining 4 for the final blank. I think that's going to be 840, but we'll check. 7 times 6 times 5 times 4 gives me 840. So what is 7 to the 4? 7 to the 4 is 2401. 2401 is greater than 840, and we're asked for how many more arrangements can be formed. So the answer to this question will be 2401 minus 840, which is apparently 1561. Number 7, consider a 6-digit numeral, and I've got in brackets here a note that 024356 is not a 6-digit numeral. It's only a 5-digit numeral, and my point is a numeral that has 6 digits cannot start with a 0. If the leading digit is 0, it's not a 6-digit numeral. It's a 5-digit numeral. So one of the conditions is this cannot be 0. We're asked for how many odd numerals have no repeating digits. Well, an odd numeral must end in an odd digit. And I just have the 10 digits in our math system written down here so that you can look at them. There are a total of 5 odd, 1, 3, 5, 7, and 9 are odd, and 0, 2, 4, 6, and 8 are even. So how many different ways can I fill in the final blank? There are a number of ways I could do it. I could use a 1 or a 3 or a 5 or a 7 or a 9. There are 5 ways to do it. Now, how many different choices do I have for the first blank? I've used one of these digits in this box, which leaves 9 digits, but one of those digits that's left over is a 0, so this is 8. And you're going to have to think about this. I'm going to repeat what I just said. I've chosen one of those 10 digits to go in the end blank. And the digit that went there, I don't know which one it is, but I do know it's one of these 5. So one of those 5 digits is out of the pool of items I can choose. And by the way, we can't repeat, so that's why it's gone. Now I have to decide of the 9 remaining digits, how many am I allowed to put in the first blank? Well, not all 9, because one of those remaining digits is a 0. So that means I have only 8 to choose from. How many digits do I have to choose from for this blank here, for this next blank? Well, the answer is 8, because I've chosen 1 digit for the end, I've chosen 1 digit for the beginning. That means I'm left with 8, and then 7, and 6, and 5. And we have to multiply all of these numbers together. And I have the answer figured out already. It's 67,200. I just want to double check that though. Eight times 8 is 64, times 7 times 6 is 42, times 5 times 5 is 25, and that's correct, 67,200. If I can get you to turn the page, please, the top of page 3, there's a note here that we need to understand. First of all, we already know the first rule. The first rule is the word and means multiply. And that's just the fundamental counting principle. Bobby Bear has to wear a pair of pants and a shirt, so you multiply the number of pairs of pants times the number of shirts. But there's another rule, and it's that the word or means add. And as we get deeper into the unit, you'll gain an appreciation for why that works. Let's take a look at the next question. Students in a class are graphing rational functions that look like that. There's a factor of x minus 9 and a factor of x minus 3 in the numerator, and then in the denominator is x minus a and x minus b. They are asked to select numbers from the list below for a and b to produce a number of different rational expressions. But all of the functions they create have to have one whole and one vertical asymptote. And if you look at the numerator of this expression, there's a factor of x minus 9 and a factor of x minus 3. And that means that the whole has to either be at x equals 9 or x equals 3. And it's either. It's not both. We're not having a whole at 9 and a whole at 3. It's a whole at 9 or a whole at 3. So what we're going to do is find the number of functions that have a whole at 9 and the number of functions that have a whole at 3 and add them together. So we need to choose something for each of the two parameters of a and b. Well, first of all, if we have a whole at 9, one of these parameters must be a 9. This has to be the number 9. And there's only one 9 in the list. Now, it doesn't say here that we can't choose the same number again, but we can't really choose 9 because if we do choose 9, we won't get an asymptote because 9 is where the whole is at. The other thing is that this second digit cannot be a 3. So this cannot be a 9. It cannot be a 3 because the 9 is where the whole is. And if we put that second parameter at 3, then we get another whole, and we want a whole and an asymptote. That means of those 10 digits, we only have 8 to choose from here. So if the whole is at 9, the asymptote could be at 1 or 2 or 4 or 5 or 6 or 7 or 8 or 0. But it cannot be at 9 and it cannot be at 3. If you do the same thing over here, I'm not going to spend time explaining it again. You're still going to get 1 and 8. You're still going to get 1 times 8 plus 1 times 8. You're going to get a total of 16. How many ways can 3 books on physics, 4 books on chemistry, and 5 books on biology be placed on a bookshelf if books from each subject must be together? This is Joan and Emily blown up out of control. What we have is the following. We have 3 physics books. We have 4 chem books. And we have 5 bio books. And because all of the books on physics need to be together, and all of the chem books need to be together, and all of the bio books do as well, what we are actually arranging is 1, 2, 3 items. And that means it's 3 factorial. Except that for this group, you also have to arrange those 3 items, those 3 physics books. For this group, you also have to arrange the 4 chem books. And for this group, you have to arrange the 5 bio books. So you have to arrange the 3 groups, which is that, And then within each group, you have to arrange all of the items. So you need to figure out what 3 factorial times 3 factorial times 4 factorial times 5 factorial is. And I already have the number here. I'll just verify it quickly on my calculator for you. 103,680. 3 factorial is 6 times 4 factorial is 24 times 120, which is 5 factorial. As you learn what some of these factorials are equal to because you use them frequently enough, it's a time saver. You're not poking around looking for that factorial function. So 103,680 different ways. And we're going to round things off with one final example. A computer store sells computer packages, and a package contains some options. You can choose of any one of 3 computer towers, any one of 4 monitors, and there are also 3 printers to choose from, and you can include a printer or not. So this is a situation where you need to choose, you need to make a decision about the monitor, you need to make a decision about the tower, and you need to make a decision about the printer. So how many different choices do you have for the tower? This is the tower. The answer is 3. How many different choices for the monitor? The answer is 4. How many different choices do you have for the printer? The answer is 4, because you can choose printer A, printer B, or printer C, or no printer. The fact that you have the option of not choosing a printer means you have 4 different answers to the question, what do you want for a printer? Printer A, printer B, printer C, or not a printer, and that's 4 options. So we work this out, and 3 times 4 is 12, times 4 is 48. I'm always leery about teaching this through video because I can't look at your faces, I can't get reactions from you, I don't know if you have questions. But again, I think this is better than just giving you a handout and expecting you to figure it out on your own. So I hope that was helpful. You can see what the assignment is. There are a number of exam-style questions there. Help each other out, work on these problems, do your best, and I will go over any questions that you have when we see each other on Monday. So I hope you have a great rest of the day and a fantastic weekend. We'll talk to you all later.